All right, let's get started. Can you guys see this? Or is the light too bright? No, it's fine. Okay, I'm afraid to pull up that screen because last time I pulled up that screen, somehow that one got messed up and it stopped displaying. You have an interesting dependency here. Maybe one of the screens is writing to a shared variable that is messing up the other screen. Maybe we have a bug here in parallel program. Okay, so this is just a reminder. These are the assignments this week, and I'll give you more assignments at the end of the lecture. You know that these are due tomorrow, right? And several of you indicated that you already started it. So take this as an opportunity to look at the ISCA program this year and see the variety of research topics that you can choose from for your literature review, as well as research projects. And there's an NVIDIA talk today. It'll be on CUDA, on the next generation Kepler architecture. Hopefully it should be interesting. And you'll have pizza, from what I hear, and refreshments. Okay, how many of you have found literature survey and project partners? Many of you. Not all of you, though. So I'd encourage you to do that very soon, too. Okay, so you know what to do for the ISCA reviews. And this is the NVIDIA talk. These are just reminders. And this is important, how to do the reviews. I've seen some reviews, they can be more detailed. They were relatively short. So you know who you are probably if you've done those reviews. It's important to cover the strengths and weaknesses thoroughly. And I'll monitor the website to look at some of your reviews. And maybe we can discuss some of these papers in class as well. Does that sound good? Especially if there's a paper that you think is really interesting at ISCA, bring it to my attention, and we might have a discussion at some point. Okay, these are all reminders. And be critical when doing the reviews, because that will lead you to actually develop new ideas. It's always good to be critical. And more information we'll provide on your literature survey. But keep thinking about this, because this will come very quickly, just like your project proposal. Okay, and these are some of the supplementary readings. Hopefully you will reference throughout the course. I really like reading this over and over when I have time. You and your research, that's a great reference on what you should be doing when you're doing research and what are some of the important things. And some things you may not consider important are actually outlined very well in that particular talk. For example, the importance of actually delivering talks and delivering clear talks. Many people underestimate that, but that's very important. And this will be helpful for writing your reviews, and these will be hopefully helpful in writing your research papers at the end of the semester. Okay? How many of you have looked at these? Oh, good. Some of you have. Maybe we'll make this a required reading. That should be a required reading for everyone, actually. Everyone who's doing research. In any area, I think. It doesn't matter. It just happens to be in computer science. Okay, student info sheets. I see many people here, and 19 people are registered, but for some reason I got only 14 of these sheets. I guess either they disappeared or some of you have not turned it in. But please turn this in, because this is important, and your grading will be predicated on it too. I know you don't care about grades at this point, but at least I'll get to know you better this way. Okay, so today we'll jump into some basics of parallel processing. And this will be review for some of you who've taken 447 from me, and maybe 740 also. Although in the last 447 we covered much of this material. Maybe not in 740. But that means that you can actually ask harder questions to me, right? Because you already know the material, hopefully. This is not required, but I would strongly encourage you to read these two chapters and Han will put these up, if he hasn't already done so, on the website, the PDF copies, scanned PDFs, on the website so that you can access these 2 chapters from the Hill, Jupi, and Soy book. This is essentially a collection of readings in computer architecture, but they have, it's divided into chapters. And in each chapter, there's a prologue, if you will, that describes the area to you, introduces the area. And we will mainly occupy ourselves with multiprocessors and multi-computers in the next few lectures. And then we will at some point go into data flow and multi-threading also. So you should definitely read this, because next lecture, if not this lecture, will be based on, partly based on that chapter. And, well, I'll override this with at the end of the lecture by giving you many more readings. You're looking forward to that, hopefully. And Color and Sync, chapter 1, is a good reference material. It's a little bit long, but it covers a little bit more than what this short 6-page, or I guess 9 pages, 9 or 10-page document covers. OK, let's start with the basics. I guess since this is a parallel computer architecture course, the first question you should probably ask is, what is a parallel computer, right? Any thoughts on this? No? Every computer is a parallel computer today, perhaps, right? OK, so the definition of a parallel computer is actually not really precise, it turns out. I'll give you one definition from Almaty and Gottlieb book from 1989. They say a parallel computer is a collection of processing elements that communicate and cooperate to solve large problems fast. I guess if this was a law class, this would probably fail that class in terms of preciseness, right? Precision. Because what is large? What is fast? What is a collection? It's not clear, right? Does 2 constitute a collection? Or is 1 a collection? I don't know, probably not. But large and fast can be all relative, right? So this is an imprecise definition. And based on this, actually, a superscalar processor is a parallel computer, too. You know what a superscalar processor is, right? We've covered this in 447 and 740. Basically, a superscalar processor is a processor that can, in hardware, fetch, decode, and execute and retire multiple instructions per cycle. A VLIW processor is also a parallel computer. So one could argue that pretty much every computer is a parallel computer today, unless you're not doing this. I mean, in this course, we're going to limit ourselves a little bit, although I don't necessarily want to limit it. I'll define a parallel computer as a processor that gives well, I guess I'll define a sequential computer this way. A processor that gives the illusion of executing a sequential ISA on a single thread at a time. That's the sequential machine definition. And almost everything else we will consider a parallel computer. And even this is arbitrary, right? Make sense? Is this clear? At least it's a little bit better than this definition, I think, because you can fit pretty much everything in this definition. So examples of parallel machines are machines that have multiple program counters. For example, based on this definition, a superscalar processor that has a single core and that is not multi-threaded is not a parallel computer. Right? It's a sequential computer. But if you have multiple program counters, then you have a parallel computer. And you can have multiple program counters in different ways, right? You can have multiple processors put together that can communicate with each other. You can have multiple threads executing on the same hardware substrate, and you've seen that many times. Multi-threading, hardware-based multi-threading. Or you could have multiple cores on the same chip, again, sharing some parts of the hardware. Also, multiple data being operated on simultaneously. That's also a parallel computer, right? And some combination of this. So we'll hopefully get to this in a little bit more detail. Do you guys remember this paper? Flynn's taxonomy of computers? How many of you do? Some? Good. The others are sleeping probably, or were sleeping when I lectured in 447 or 740. So this is a seminal paper that was written in 1966. And it basically classified computers in two dimensions. One is instruction and the other is data. And a computer in which you have a single instruction operating on a single data element, all instructions are like this, is a SysD computer. Single instruction, single data. That's not very interesting, and we've covered that. And that's obviously not a parallel computer, right? If the only thing you have is a SysD. We've also covered SIMD a lot, which is single instruction operates on multiple data elements. And you should know this from 447 and 740 very well. An array processor and a vector processor, or existing GPUs, for example, are SIMD machines, where you have instructions operating on a single instruction operating on multiple data elements. All those GPUs programming models are a little bit different. We'll get to that. And there's also a MISD machine, which I will get to after this, perhaps. Let's take a look at MIMD, though. You have multiple instructions operating on multiple data elements in parallel. Basically, multiple instruction streams, if you will. So this is the most classical definition of a multiprocessor. When people talk about multiprocessors, they're really MIMD engines. And that's a parallel computer, or a multi-threaded processor. That's also a MIMD engine. SIMD is also a parallel computer. MISD, we will cover the closest form to it. MISD, multiple instructions operate on single data element. How could this be possible? Right. Any ideas? This is probably the most weird form of this taxonomy. So one thing we will cover later on in this course is a systolic array processor, a notion that was actually developed at Carnegie Mellon by H.T. Kong in the late 1970s and early 1980s. And the idea is basically you input data into a series of processing elements, and each processing element executes an instruction. You could think of it that way. And data gets input to the first instruction. That instruction produces the result. That gets input to the next instruction. It's a systolic array. It's an array of processing elements. And we will cover that in more detail. Basically, you have data coming in, streaming through different instructions. And essentially, you have multiple instructions operating on the same data element and outputting the data outside somewhere. This is one form of, I guess, closest form of MISD, if you will. And there are processors that were designed, specialized processors that were designed to do signal processing, for example, image processing this way. You can take an image. You can actually have two-dimensional inputs going into this array. And you can get two-dimensional outputs, right, from this array. Yes?
How's this different from just that pipeline?
So it is essentially, it is similar to pipelining, except now you have different instructions operating on the data.
Oh, so
it's not the same instruction.
You can select what all those instructions
That's right, exactly. You could do that. And more general form of it is actually you could have a function, right? You could have a program 1, program 2, taking the data, operating on it, producing the result, passing it to another program, taking data, operating on it, producing results. And that's the streaming model of computation, if you will. And we will get to that also. Okay? Any questions on this? So I would argue, well, these three forms of this part of the taxonomy, if you will, constitute the parallel computers. And I think anything in here should constitute the parallel computers. That's probably a more precise definition. Okay. So now we've somehow defined parallel computers, but why do you need them? Well, parallelism, at its most general definition, is doing multiple things at a time, right? Because you guys are parallel processing engines also. Hopefully you can do multiple things at a time at any given instant. Things could be instructions, operations, tasks, threads. What is the main goal of this? I heard something like speed up. Yes, improving performance, right? Either execution time or task throughput. That's the main goal. And execution time is, you know very well, hopefully, from the very beginning of your education, that Amdahl, it's covered by Amdahl's law. Right. And we'll get back to that today. But if you haven't read the paper, I'm not going to assign it. You should read that paper. Well, if you've taken 447 and 740, you already read it, hopefully. But there are other goals in designing a parallel computer. And you've seen the slide last semester if you've taken 447, so you can tell me what those are. What could be another goal? Redundancy. That's interesting. Meaning, why do you want redundancy?
So, like the IBM C-series, in their mainframes, they have two processors that read in the exact same instruction each time step to do the same thing.
Mm-hmm.
Actually, can do the same thing. Check to see if it is the same thing. If it is, go out the result. Otherwise, review the computation.
Okay, so that's very good, actually. Basically, the goal in that case is to improve reliability or dependability of computation, because if you have only one processor, you may get a fault and you may get the wrong result. But if you have 3 of them, you can do the same computation on all 3 on a parallel computer, and you can check the result, right? And that is actually one goal. That wouldn't be the first goal people would come up with. And actually, I have a hard time having people come up with that goal. But that is one goal, you're right. Yes?
Reduce the clock frequency on the processor.
So, that's right, that's a mechanism.
Lower power.
Yes, low energy efficiency, higher energy efficiency, right? Reducing power consumption. That's another goal. Your goal will come up at the very end, because usually people come up with that one the last, if at all. But yes, one other goal is reducing power consumption. And I'm not going to go into detail because we've covered this in 447 and 740 before, but the idea is if you can parallelize your work, instead of having, let's say n equals 1 here, 1 unit that operates at frequency f, you can have 4 units that operate at frequency f divided by 4. If you can parallelize your program, your execution time doesn't change, but your energy consumption reduces. Right? Why? Because as you reduce your frequency, you can reduce your voltage also. And if you remember the power equation from our previous classes or other classes, dynamic power is proportional to this, right? CV square F. C is the capacitance, V is the voltage, and F is the frequency. As you reduce frequency, you can usually reduce the voltage. That may not be true today as much. And you can get a cubic reduction in power because of this. And you don't change the execution time if you can parallelize your program perfectly. That way you get a significant reduction in power consumption, which translates to significant increase in energy efficiency. And this is one of the reasons why a lot of companies went to multi-core systems. It may not be the only reason. Okay, so you got 2 of the goals: reducing power consumption and improving dependability. I think there's one more left. There's space for one more here, right?
Is it to scale to larger problems?
Scale to larger problems. I guess that's, I would argue that's similar to improving performance, right? But that's true. I mean, that's definitely a goal, because you cannot improve performance more than a single processor. I think you kind of captured this. Improve cost efficiency and scalability. Reduce complexity. I think these all go together, if you will. Harder to design a single unit that performs as well as n simpler units. So you're right. right? In fact, I would argue that this is the main reason why people started building multi-core processors, because it became very hard to design a single core that performed well. It was a lot easier to design n simpler cores, and for those problems where you can actually parallelize, you get better performance. Make sense? Okay. Any others? I don't have space here, but if you find any other fundamental reasons why you do parallel processing, let me know. That doesn't fit into any of these. So far, no one has come up with it yet. Yes, you're going to try.
I just want to add to the power consumption part. Sometimes the power density is also an issue. So if you fit things on a smaller die on single chip, the power density per unit area becomes more. There may be no system to handle the heat dissipation for that. So you may want to distribute the task so that the area also spreads if you have free area on your silicon.
Okay.
And the other thing with power consumption only, you can have a slower code which you can use for low performance work. If you have some background work, you can put the high performance cores to sleep and let the low performance core, which consumes less power, perform the easy work.
That's right. I mean, you can improve power consumption in different ways, but they all take advantage of parallelism, right? Maybe you take advantage of you have different frequencies, but that's still taking advantage of different parallel processing units that are existent on the chip. Okay. So let's talk about different types of parallelism. I'll cover this relatively quickly, because hopefully you know many of this from previous classes. There are three major kinds of parallelism. Instruction level parallelism is one, data parallelism, and task level parallelism. In instruction level parallelism, different instructions can be executed in parallel in a single stream. And you've seen this in 447 and 740. We see many techniques to improve ILP. Right? Pipelining, out-of-order execution, speculative execution, branch prediction, for example, VLIW, and data flow, which we will see in more detail in this course, exploit instruction level parallelism. In a single stream, you can execute multiple instructions in parallel. Data parallelism is a different kind of parallelism. Now you have different pieces of data that can be operated in parallel. And you could be doing the same instruction on all of that data. And SIMD takes advantage of that. And we will cover this. In task level parallelism, your parallelism granularity is coarser. You have different tasks and threads that can be executed in parallel. And we will occupy ourselves a lot with that, with multi-threading and multiprocessing. Let's take a look at the different forms of task level parallelism also. One question is, how do you create tasks, right? You could think of task level parallelism as taking a single problem and dividing it into multiple tasks. Or taking many different problems and executing them together, right, in a mix. That's what a lot of people are excited about today. Let's take a look at the second one. You can get tasks by running many independent tasks together. Right? I can take tasks from every one of you and execute them on my parallel computer and hopefully give you good results in the end. Well, I guess this is easy when there are many processes, like all of you need to do some job at the same time, right? For example, batch simulations, if you have different users doing different things, or cloud computing, right? That's what cloud computing is all about. It's essentially a big multi-program workload executing on a system. The downside of this is it doesn't improve the performance of a single task. If you create tasks this way, you basically need to wait for independent tasks to somehow arrive. Right? But if you have a single problem that you need to solve, then you somehow need to create these tasks. Right? And there are two ways of, basically, you need to create these tasks that are related and that cooperate to solve that single problem. You could do this explicitly by doing parallel programming. Have you all done parallel programming, by the way? Programmed with threads? Yes? If you've taken an operating systems course, you should have, hopefully. Or you should have written even the infrastructure to actually execute those threads, right? The fork system call. Yes? No? No? Okay. Maybe you should take an operating systems course. It's a lot of fun. Okay. So when you do parallel programming, you basically create these tasks explicitly. This is easy when the tasks are actually natural in the problem. It's difficult when the natural task boundaries are not clear, right? How do you actually divide a single program into multiple pieces? And we'll talk about some of this. Another alternative, which we will also cover in this course, is actually we'll spend a lot of time covering this, is how can you actually transparently parallelize a single problem? And I'll collectively categorize all of those approaches as thread level speculation, even though they may not be speculative necessarily. Basically, you have a single threaded program, and you speculatively or non-speculatively divide it into pieces automatically. And we'll see what research is in that area, what research has been done in that area. This could be actually an interesting place to do your projects if you're interested in it. Yeah, talk with me if you want some references on this. Okay, any questions? Okay. Well, let's MIMD processing. If you remember, MIMD is multiple instruction, multiple data. I guess I cannot go back to it, but it's essentially multi-threading and multiprocessing. And there are two forms of it, which we will cover in a little bit detail. It could be at least the hardware that's designed to do multiple instruction, multiple data, multiple processors, can be loosely coupled or tightly coupled. Do you guys remember what these were? This was a 447 exam question, I think. What's the key distinction between a loosely coupled multiprocessor and a tightly coupled?
Whether they share memory.
Okay, that's good. Whether the processors share memory. In which one the processors share memory? Tightly coupled, exactly. So tightly coupled multiprocessors, they have shared memory, shared global address space, if you will. Whereas loosely coupled multiprocessors, they do not share memory. There's no shared global memory address space. And this is everywhere, right? The multi-computer network, network-based multiprocessors. They're essentially loosely coupled multiprocessors. And usually these systems are programmed via message passing. It's essentially a distributed system, right? If you have ever programmed distributed systems, you do messaging between different processors. Basically, for communicating between processors, if you divide a task into multiple processors, to communicate between different subtasks, each processor needs to send and receive messages. I say usually here, but it's not always, right? So we will get back to this maybe later in this lecture. This is really the hardware substrate, right? The hardware substrate does not have shared global address space. But that hardware substrate may not be visible to the user, right? We have abstraction layers today. You could, so your hardware may be loosely coupled, no shared memory. I guess I'll overwrite this power equation. But your programming model may have shared memory. But you can still perhaps execute this program on this hardware. Right? Why? Because there is a translation layer or abstraction layer in between that can essentially take those operations that happen on shared memory locations and translate those into messages, send and receive. Right? So we will cover this. This is the decoupling of the programming model and the hardware. But right now I'm talking about hardware here. Okay, so tightly coupled multiprocessors, there is the key is they have a shared global memory address space. And when people talk about traditional multiprocessing or symmetric multiprocessing, that's tightly coupled. So you'll hear the term SMP. most existing multi-core processors and multi-threaded processors are tightly coupled multiprocessors. In this case, the programming model is similar to uniprocessors, right? You have a single memory address space, and you do loads and stores. When the tasks communicate with each other, they can store to a location that's visible to everybody else, every other task, every other processor, right? Except when there are operations on shared data. Let's say you have two processors that are accessing the same memory location. Somehow you need to synchronize between them. OK, that's the difference between this programming model and this programming model. But we'll get to this. We'll cover tightly coupled multiprocessors a lot in this lecture. And this is kind of an overview, if you will. Not in this lecture, in this class. But this is kind of an overview of some of the major issues in tightly coupled multiprocessing. We'll talk about shared memory synchronization, locks, and atomic operations. We'll talk about cache consistency, which you should already know about, cache coherence, better known that way. We'll talk a little bit about ordering of memory operations. You guys remember sequential consistency from 447? Yes? Maybe. OK. Maybe we'll cover again then. Maybe we should have a pop quiz on what sequential consistency is. All right, we'll get back to it. We'll talk about resource sharing, contention, and partitioning. That's an important issue in tightly coupled multiprocessors. Like, how do you handle the shared resources? How do you communicate between these different processors? And how do you handle the load imbalance? This is an incomplete list, but hopefully we'll develop a much more complete list as we go along in this semester. So I'll take an aside here. We've been talking about multiprocessors, and that's one form of MIMD, multiple instruction, multiple data processing. But there's also a very common form of MIMD, which is hardware-based multithreading. Right? A lot of the hardware you have today on your laptops, for example, is capable of executing multiple threads on the same pipeline, if you will. Right? And that's hardware-based multithreading. And this could be done in 3 different granularities. One is coarse-grained, so you can have multiple threads that can be switched in or out the hardware at coarse-grained intervals. Thread A can be running for a while, and after 1,000 cycles, thread B can be executing. And after 1,000 cycles, thread C can be executing. Right? That's what operating systems do, for example, right? If you have multiple tasks. And except the quantums are not 1,000 cycles in that case. Quantums are on the order of milliseconds. And that's not hardware-based multithreading because you have only one context. And the operating system saves and restores the context at the quantum boundaries. But if you want to do it at a much finer grain, yet still less finer grain than this part, you need to have hardware support for multiple contexts, multiple thread contexts. And you remember this very well, hopefully. On the other hand, fine-grained multithreading, it has a special meaning, is cycle by cycle. Every cycle, you fetch from a different thread. Now, this obviously requires that you have multiple thread contexts. And hopefully you remember the benefits of this. One benefit is if you have enough threads, if the number of threads is greater than the number of pipeline stages, if you will, or greater than equal to, now you don't need any dependency check logic, right? Because you know that there will be no 2 instructions that are dependent on each other, at least at the register level. You know that you don't need to predict the direction of a branch to keep the pipeline full, because you're not going to fetch the next instruction from the same thread until that branch is resolved. That's the benefit of fine-grained multithreading. Except it requires that to keep the pipeline full, you have to have enough threads. Right? And if you haven't read this book, you should read it. It's a little bit tough to read. It's Jim Thornton. This is, I don't know if you guys know about CDC 6600. How many of you do? This was a computer that was designed in the 60s. The book was written in 1970. Jim Thornton was the chief architect. And CDC stands for Control Data Corporation. It's a Canadian company. that was competing with IBM at that time in building supercomputers. And this was the supercomputer of the time. This was actually a supercomputer that had out-of-order execution. And this book describes the design of it. It was actually faster than the computers IBM built at the time. The small team of engineers built this computer that was faster than IBM 360 at the time. And at some point, IBM came up with 36091, which included Tomasulo's algorithm, which is the out-of-order execution algorithm that's a version of which is used in many computers today. Right? But that's a good book to read, actually. And that was the first computer that actually employed fine-grained multithreading. It turned out in that computer, the I/O, or memory access latency, was 10 cycles. And they wanted to tolerate this latency, so they had 10 threads. Each thread could start an access every cycle. That way, you could cover the latency. You can tolerate the latency by having 10 threads, right? That's where they employed the fine-grained multithreading. And I will assign this paper later on, probably. Have I already assigned this paper? I think maybe I assigned a later version of this in 740 or 447. Multithreading became a lot more popular when people tried to design very large-scale supercomputers, because multithreading is a way of tolerating latency. And if you're waiting for memory all the time, if you're doing a lot of data accesses, if you have a lot of threads, you can tolerate that latency. And this paper describes basically fine-grained multithreading done on a processor pipeline. And we'll cover that in more detail. OK? I guess this aside is taking longer than I thought it would be, but that's good. Any questions? You guys should be asking questions, too. Otherwise, I'll assign more readings. OK. There's also simultaneous multithreading, which a lot of people confuse with fine-grained multithreading. They're not the same. Simultaneous multithreading is a specific form of multithreading where you can actually dispatch instructions from multiple threads at the same time. So it's more aggressive than fine-grained multithreading. Here you can actually send 2 instructions from 2 different threads to 2 different functional units at the same time in the same cycle, which requires that you have multiple functional units. Right? Whereas fine-grained multithreading doesn't require that you have multiple functional units. You can have a single functional unit, and you can interleave execution on that functional unit cycle by cycle. Yes?
The fine-grained multithreading still requires a lot of scoreboard techniques, right, to maintain the differences between the different threads, so that you don't, assuming that the hardware takes care of that and not the programming themselves.
What do you mean scoreboard?
So like, there's like 10 threads, and each thread has to have its own sort of private reserved like register space.
That's right, yes. Yeah. You need to have the context, which consists of your registers, architectural registers. Yeah. In hardware, you need to have that. Yes?
The simultaneous multithreading is kind of orthogonal to first two, right? You can have a 17N one on the other.
That's right. That's right. Yes. That's right. You can actually combine all of these, perhaps, in many different ways. OK. I guess you start asking questions once I said you'll have more readings. Any other questions? That way we don't get to the last slide, which lists all the readings. OK. Let's talk about caveats of parallelism. It's always good to start with know what are the limits of what you can achieve with a particular solution. That's why I want to present first caveats. And you already know this, right? Amdahl's law. And if you haven't done so, you should read this paper. But if you've taken my classes, you've already read this paper. It's Amdahl's original paper, which basically stated this law. And the law states that the speed up you can achieve with n elements is this. Basically, P is a parallelizable fraction of the program, and n is your number of processors, your speed up will be 1 divided by 1 minus p plus p divided by n. Right? So the assumption is that the parallelizable fraction of the program, parallelizable part of the execution time of the program, can be divided perfectly among the n processors. Right? And this is the serial part of the program. You cannot do anything about it using parallel computers. It's a simple model, which means that your maximum speed up you can get is limited by the serial portion. Right? So this is your serial bottleneck, if you will. If your p is 99%, your maximum possible speed up is 100. Right? I'm not going to go into detail, so you hopefully know how to do that calculation. Make sense? If your p is, I don't know, 50, your maximum speed up is 2. So hopefully your p is not 50. But when Amdahl wrote this paper, if you can see what the title says, validity of the single processor approach to achieving large-scale computing capabilities. He examined some programs and he saw that p was not close to 99. P was more like 60, 70, 80. As a result, he thought you cannot achieve large speedups, at least on those problems, in the way people were programming them with parallel processing. So you better design a processor that improves this part, basically single processor. Okay? That may not be true for all problems, and we know that that's not true in many problems that we see today. Right? That's one of the reasons why graphics processing units have been very successful. In graphics, p is very large. In fact, the sequential portion is small, but you're still limited by the sequential portion, right? Your p can be, I don't know, 0.99999. And still you're limited by this. In the limit, your speed up is limited by that 1 minus p. Okay, so this is actually a nice abstraction, but we'll look at other caveats. So that's one caveat, serial bottleneck. And we will cover this in more detail. Almost all parallel machines, all parallel machines had the serial bottleneck. This was a problem. And if you remember my lectures before, actually, one test question I'll ask you now is, if you remember Cray 1. Cray 1 had the fastest scalar unit of its time. Right? The frequency of its scalar unit was the fastest of its time, faster than any of the sequential processors. Cray 1 was a SIMD processor. It was a vector processor. But they designed the scalar unit to be very fast. Why? Yes, you're attempting it.
Because if they have a fast single processor for the serial portion of the code, they will achieve better speedups.
Exactly, yeah. The reason they designed that scalar unit to be fast was because they were concerned with the serial bottleneck. They wanted to overcome that serial bottleneck. Because they were doing very well with a large SIMD unit, but they were not doing very well with a slow scalar processor on the serial part. And parallel machines always have that serial bottleneck. So if someone tells you that they've designed a parallel machine that's perfectly parallel, don't believe them. They're going to have the serial bottleneck. Okay. On top of this, parallel portion is usually not perfectly parallel also, right? If you look at this assumes that your parallel portion execution time will be divided by n. But based on what we've discussed in the last lecture, you know that that's not true, right? There are 3 reasons why this is not the case. Anybody remember those? By heart? Yes, Joe. Okay, that's a good try though. Remember the parallel task assignment problem from last lecture? There was a load imbalance problem, right? If your load is imbalanced, you cannot divide it by n because you're not perfectly parallelizing your tasks across different processors. That's one.
Different synchronization between.
That's right. The second is the synchronization overhead. If the parallel tasks are accessing some shared data, they need to wait for each other. Right? They cannot update the same shared data at the same time. And that leads to, now you cannot divide this by n again, because there's some portion of time where you're waiting for other threads to update the shared data. So that makes 2. What is the third one? That's right, resource contention. Right? If the parallel tasks are contending for a resource, now again they need to serialize. They need to wait for each other. You can think of load imbalance as some kind of serialization also, right? You haven't divided your load well, so the latest finishing tasks is a serializing point. So these are 3 fundamental overheads that make parallel portion not perfectly parallel: synchronization, load imbalance, and resource sharing. So never forget these. And if you find a 4th one, then you probably found the memristor or something like that. The 4th element that didn't exist before. OK. Do you guys remember this from 447? OK, so I guess let's go through this exercise because it's very fundamental. Well, I guess this is hiding here. I'm afraid to turn off this. I'll turn it off after I write the problem. So it's basically we have this polynomial computation, and I did a terrible job making these subscripts. A4 x to the power of 4, A3 x to the power of 3, A2 x to the power of 2, plus A1 x to the power of 1, plus A0, where a's are constants and x is a variable. I'll ask you this question. Maybe you can take 5 minutes of your break to answer the question. You can assume each operation takes 1 cycle, and you can see how many operations there are. There are some additions and there are some multiplications, right? You multiply A1 with x, and you need to get the square of x and multiply it with A2. And assume no communication cost, and assume processors that can execute 1 operation. Each operation can be executed in a different processor. I guess how long do you take to solve this polynomial with a single processor? That's the first question. And the answer should be some number of cycles. And the second question is, assume that you parallelize this. You have 3 processors. How long do you take to execute this computation? With these assumptions, no communication cost. So for example, if you execute A1 times x in one processor and the addition, and A2 times x in another processor, when you do the addition, there's no communication cost. It's magic. It's nice. Are you guys attempting it? While you're doing that, I will turn off the write display. This is the write display, right? Or put the screen up. And hopefully that doesn't interfere with this screen. Good. So far it worked. It'll take a couple of minutes. I'm always amazed when students are able to do this in their heads because I can never do it in my head. And I guess the third question is, what is the speed up of 3 processors over 1 processor? I guess that's easy to do once you calculate the answers to the first 2 questions. And we could use this as our break time. Don't cheat by looking at the lecture notes from last semester. I guess I'll tally the answers here. I guess 3 processors. Are you coding it? You could write a program that figures this out, right? Anybody got the answer? Let's wait one more minute, I guess, so that the break is over. We didn't have class last Friday, so it's a good break. And you can collaborate. That's good. You guys are doing the right thing. How many people got it? Some? Only one? Okay. I'll give you one more minute. Okay, what is the answer for the single processor? Jamie, or either of you?
We say for one processor, the
8 cycles for one processor. Oh, that sounds like magic. Who else? 14 for one processor. What else? 11? What else? That's it? So I guess we have 8, 11, 14 for one processor. How many people say 14? Raise it up. 1, 2, 3, 4, 5, 6, 7. 7? You say 14? Okay, I'll do 7. This is kind of an odd way. How many people say 11? 1, 2, 3, 4. That's it? Okay, 4. How many people say 8? 1, 2, 3, 4. Only 4? Those of you who've taken 447. How many people abstain, I guess? Is this 7, 4, 4? There are more than 15 people here. That's okay. You have stayed. What about 3 processors? Yeah, what is 5 cycles? 5 is one suggestion. What else? 4 cycles. Wow. Okay. I have to see that solution. 6. That's it? So who said, how many people say 4? 1? Is this approximate computing? does it give the right answer? How many people say 5? Okay, that's a large majority. How many people say 6? 1, 2. Okay. So I'll just put around 10 here, if you will. I didn't count, but it'll take a while. Okay. I really would like to see this 4 solution. Maybe there is a mistake here, but you don't need to do it right now. We can do it later. But most people, when you give them this problem, actually, I guess there's one lesson out of this, which is optimizing a parallel program is difficult. Because, or even a single program is difficult because you get so many answers, right? I think the best parallel program should be 5. And the best single processor program is actually 8. But most people, when you give them this, they usually come out with 11. In fact, that's probably the most natural thing. So let's take a look at how you come up with 11. This is how you come up with 11. Maybe you didn't come up with it exactly this way, but basically you have 11 operations. You factor out a1x squared. Well, a1x is here, and then a2x squared is here, and then a3x cubed is here, and then a4x4 is here. So you basically have the x squared, x cubed, x to the 4 dependence chain here, and then the additions here, if you will. And you get 11 cycles. And this is a valid data flow graph. And that's what most people would come up with. I don't know how you guys came up with 14, but there's a better way of doing it, as you can see here. And with 3 processors, this is why I'm baffled with the 4-cycle answer. This is the best you can do, as far as I know. Basically, this is how you would parallelize. And it takes 5 time steps, unless you omitted an operation. OK, good. So this is an approximate answer, which may or may not be correct, depending on the value of x or a. OK, so this is t equals 5 cycles. And your speed up, essentially, if you do these 2 things, is 11 divided by 5, 2.2, with 3 processors, which sounds pretty respectable, right? But is this a fair comparison? That was the purpose of this exercise, actually. But we figured out something else, which is parallel programming. Optimizing for performance in parallel programming is difficult. And optimizing for correctness may be difficult also. These are all issues, actually, in real parallel programs. This simple example demonstrates. Even if you don't have any of these overheads that we discussed, the communication overhead, synchronization overhead, optimizing for performance is difficult. Optimizing for correctness is difficult. And that's what this course is really about. But there's also something else that I want to point out in this example, which is the fair comparison. If you do this comparison, this is not a fair comparison. Because you have not designed the best possible algorithm for the single processor, whereas you have designed the best possible algorithm for the multiprocessor. Well, what is the best possible algorithm for a single processor? You guys collaboratively found out over there, I guess, is this. That was demonstrated in 1819 by Horner. You basically factor out the x's this way using Horner's method. Have you guys learned Horner's method in high school? That's a way of factoring out polynomials. And you can basically take this polynomial, and factor out x's this way, and this is what you would get. And if you actually look at the data flow graph of these operations, you first do this calculation, a4x, and then add a3. And then you get a result and multiply it by x. And then you add a2. So you basically interleave additions and multiplications instead of doing the multiplication and addition this way, as we've seen. Right? And that's what you will get for a single processor. It's a serial dependence chain like this, but the end result is 8 time steps. And if you have 8 time steps, your speed up with 3 processors is only 1.6, because it's 8 divided by 5, not 2.2. Okay? So this is the fair comparison in this case. And this is very important, because if you add the communication overhead now, what do you think your speed up will go down to? Much closer to 1, right? Rather than closer to 3. So this, if you take it to the extreme, let's say we actually took, well, I guess it doesn't work here, but maybe you guys came up with 16 here. And we divided 16 by 5. Your speed up would be 3.2, right? 14 divided by 5 gets close, 2.8. You get 3.2 speed up with 3 times as many processors. That's called superlinear speed up. And if you hear something like this, you should be very, very wary of why that happens. Basically, superlinear speed up means speed up is greater than p with p processing elements compared to 1 processing element. And this is a pictorial depiction of it. Number of processors, the parallel speed up you get, linear curve is this. Superlinear means your speed up increases superlinearly. Typically, the speed up curve looks like this. It's sublinear. As you add more processors, your speed up it gets diminishing returns. In fact, after some point, it goes down, and we will see why it goes down. Well, why does it go down? Because of all those 3 things that we discussed: resource contention, synchronization overhead, load imbalance. And also, synchronization overhead consists of sharing data somehow and moving data around. We will get to that. So why do you get superlinear speed up? Well, there are 2 reasons. None of them are necessarily justifiable. One is unfair comparisons. That's a terrible reason to get superlinear speed up. The second reason is may or may not be easily controllable, like memory effects. For example, as you add more processors, which is not true in this this is not true in this example, but as you add more processors, you may be adding more memory also, right? And you can, at some point, get higher speed up if you add more processors. At some point, the entire working set of the problem may fit into the memory you've added, or you get better locality at some point, and then your speed up increases, right? That's still not a fair comparison, because you're not only adding processors, but you're adding memory, right? Maybe the fair comparison is your memory stays constant, and you just keep increasing only the processors. Right? That way, you don't get superlinear speed up. Okay? Any questions? And if you find out any reasons, let me know. Any other reasons? But this is very important. Okay. I'll go through this relatively fast. In multiprocessors, there are 3 things that we have defined in 447 before: utilization, redundancy, and efficiency. And these are traditional metrics to evaluate multiprocessors other than performance. And if you assume that these assume that all P processors are tied up for the parallel computation you're doing. Utilization means how much of the processing capability do you actually use? Actually, let's go to this. In this particular example, it's essentially you tie up some number of processors, some number of time steps, and how much of the processor what fraction of those time steps, if you will, are actually busy? You're doing an operation on those time steps. So if you look at the previous example, let me go back to it quickly. This is a parallel version. In this case, the first time step, you keep all 3 processors busy. In the second time steps, again, all 3 processors are busy. In the third one, 2 processors. In the fourth one, 1 processor. In the fifth one, 1 processor. So your utilization is going down, right, as you go through the time steps. And your overall utilization is essentially you have 15 possible operations processing capability during that time duration, and you're using only 10 of it. That's utilization. So you're not utilizing your parallel computer at 100% because you're not doing operations all the time. Redundancy is how much extra work is done with parallel processing. And normally your redundancy increases as you increase your parallel processing because you have overhead in terms of synchronization, right? It didn't happen in this example, but redundancy is essentially number of operations you do in the parallel version divided by number of operations you do in the best single processor algorithm version. In this case, number of operations with parallel version is actually 10, right? We use 10 of these here. Whereas number of operations with 1 processor, we figured out the best is 8. So your redundancy is greater than 1. We've increased the number of operations, even though we didn't have any synchronization overhead. So that we could exploit parallelism, we need more operations with the best parallel algorithm. And as you add more overhead, this redundancy increases. And efficiency is essentially utilization divided by redundancy. Basically, how much resource do you use compared to how much resource you can actually get away with, right? Now, what does that mean? Basically, we're tying up 15 operation units, if you will, if you look at this. We're tying up 15 things that we can use. But we could actually have gotten away with only 8 if we had a single processor, right? We could have achieved the same task only with 8 operations, whereas now we're tying up 15 operations, potential operations. So our efficiency is actually 8 divided by 15 in this case, which means that we're not that efficient, right? And you always reduce efficiency. Given that R is always greater than 1, you always reduce efficiency as you increase parallel processing capability. These are very fundamental. And if you add overhead, your efficiency goes down even more. OK? OK, I think we've kind of discussed this. Well, I guess we didn't really discuss this reality very well. But reality, the reason you get sublinear speedup, one of the reasons is, let's see. This is Amdahl's law, if you will, written in a different way. This is the time taken with P processors is equal to the serial fraction times time taken with 1 processor plus parallel fraction times time taken with 1 processor divided by P. And because you don't have this non-parallelizable part, you get this curve that's sublinear. And if your parallelizable part is also not perfectly parallelizable, this makes your curve even more sublinear, right? OK, we already talked about this. You get a bottleneck for parallel speedup. This is just for your benefit. And this is an illustration of Amdahl's law, if you will. This is number of processors on the x-axis, speed up on the y-axis. And I plotted pictorially, if you will, different values of parallel fraction. If your parallel fraction is 90%, this is the curve you get, speed up curve you get. If it's 95%, this is the speed up curve you get. If it's 98%, this is the speed up curve you get. And they all look very similar, right? Because you have diminishing returns. Right? Basically, adding more and more processors gives less and less benefit. Make sense? You can draw these curves yourself, yes?
So then what you're saying then is that those lines are getting closer together as you. What do you mean by it adds less and less?
So for a given curve, if you add more and more processors, like if you go from 59 to 60, you get less benefit than going from 1 to 2. Right? It's diminishing returns. And if you plot it a different way, this is alpha, if you will, the parallelizable portion. It can go from 0 to 1. And this is the speed up you get. And you can have different curves depending on the number of processors, right? P1 is smaller than P2 is smaller than P3 in this case. And if you plot this curve, and I would encourage you to do that if you're interested in this, the benefit is small until alpha is very close to 1. Right? That's Amdahl's law again. It says basically your serial bottleneck is your bottleneck. So unless your alpha is really close to 1, you don't get a whole lot of speed up. So you better make your alpha close to 1. Okay? So you've seen this all in 447. And I'd encourage you, everybody else to study this. But that's what Amdahl's law is about. The difficulty is making alpha, or f here in this case, I guess I should at some point make these the same, is difficult. Getting rid of the serial bottlenecks is difficult for the programmer. And also, even these curves assume that parallel part of the program is actually perfectly parallel. So yeah, these curves are plotted assuming that, which means that your real speed up requires even a higher alpha. Right. Yes? Yes?
So, alpha will have a different interpretation based on the number of processors, right? If I have 3 processors and a given program, then I should look for the part of the program where there can be 3 parallelizable threads. Let's say I have only one program. I run it on two core system.
Okay.
Then there will be some particular alpha. But if I run the same code,
Okay. So yeah, the abstraction here is that if you have a parallel part of the program, it's perfectly parallelizable. Meaning it doesn't matter. You can divide it very fluidly into either 2 chunks, 5 chunks, a million chunks, a billion chunks. That's the abstraction of Amdahl's law. And that's the downside of Amdahl's law because it doesn't take into account these effects that happen in the parallel parts. But you're absolutely right. I mean, if you your parallel parts is not perfectly parallelizable in real life. Okay, so we've already covered this. I want to cover this again here. And this is a real way of drawing that curve, if you will. If my cartoons weren't enough, this is the parallel fraction plotted here. And this is the speed up you get with different number of processors. If it's 10, this is how your speed up increases. If it's 100, this is how your speed up increases as you increase the parallel fraction. And if you look here, you don't get more than 10 speed up until even if you have 1,000 processors, you don't get more than 10x speed up unless your parallelizable portion is close to 90% or so. Okay. So I guess you could ask, why do you have these sequential bottlenecks? And all parallel machines have this. Well, because you can have non-parallelizable portion of the data. This is one way of representing computation, if you will. You have a sequential part and you have a parallel part. Basically, the sequential part can actually prepare data for the parallel part. That's one reason you have the sequential bottleneck. And there could be non-parallelizable operations on data. If you have loop carry dependencies, you may not be able to parallelize your loop. Right? And as you have more and more non-parallelizable things, this part of the program increases. Make sense? Okay. And you'll read this paper that will be assigned that shows an example, if you will, I guess from a very generic example that looks at a task tree, basically. Basically, you spawn threads initially and set up the data for each thread. That part is not parallelizable. And this is a parallelizable part of your program. While the problem is not solved, you generate new problems, subproblems. Remember the maze problem? The rat looking for the cheese? You generate new problems dynamically, in a dynamic tasking way. So this is the parallel part. That's not perfectly parallel, but the sequential part is here in this problem, and also here. It's not parallelized. If you look at the execution of this with 4 threads, this is from the accelerated critical sections paper that you will read. The execution looks like this. Sequential part, parallel part, which is not perfectly parallel in this case because you have operations on shared data, and then the sequential part again. Okay? So bottlenecks and parallel portion, let's cover this in a little bit more detail. We'll occupy ourselves a lot, especially in your readings soon. Synchronization is one bottleneck. Basically, operations manipulating shared data cannot be parallelized. Right? And you need to protect that shared data with different constructs, if you will. Locks, mutual exclusion is one way of, well, locks are one way of ensuring mutual exclusion. And basically, this ensures that threads communicate data with each other in a safe way. Right? And this causes thread serialization when the data is actually contended. Right? When there is no contention, there is no serialization. If one thread is updating data and no other thread is reading it or writing to it, then there's no problem, right? Load imbalance, parallel tasks may have different lengths. We've covered this. And this could happen due to two reasons. One is imperfect parallelization, as we've talked about last time. But this could happen because of microarchitectural effects too. For example, one thread gets a cache miss, whereas another thread is executing very fast. It has good locality. Right? And this, again, reduces speed up in the parallel portion. And resource contention, parallel tasks can share hardware resources delaying each other. You could eliminate this potentially, right? By replicating all of the resources. Each task gets its own dedicated resources. Gets its own processor, own cache, own memory. But then you run into another problem, which is it's expensive to do so. And maybe if you actually shared resources, you can get better performance because not all threads are active at the same time. Right? Okay. So resource contention leads to additional latency that's not present when each task actually runs alone. And we will cover this a lot also, especially in caches and main memory. And processing also. If you have multiple threads sharing the same pipeline, you have this problem, right? They're contending for the same functional units if you have a simultaneous multi-threading engine. OK. I think that we've covered this a little bit with this example. But parallel programming is difficult. It's actually easy if the parallelism is natural. If you have embarrassingly parallel applications, you probably heard this term. For example, graphics. Right? You have lots of pixels, and you do the same operation in every pixel. There's lots of parallelism in that problem. Right? And they're independent, hopefully, depending on what you want to do to the pixels. So there's a lot of parallelism there. And maybe some other applications are also embarrassingly parallel if you're doing the same operation on many different elements of data. But if the parallelism is not natural, then it becomes difficult to divide a problem into multiple tasks. And the difficulty is in two things. One is getting parallel programs to work correctly, as we've encountered here. And this is a real thing. I mean, this is you don't have infinite amount of resources, right? When you write a program, the programmer's time is precious, right? At some point, you have a deadline to ship the product if you're doing a product. And if your goal is to optimize for performance, you may get things wrong, and you can get into wrong programs, wrong parallel programs. In fact, a lot of the bugs you see in some of the popular operating systems are usually due to some synchronization problems that cannot easily be figured out. So that's one of the difficulties. The second difficulty is optimizing for performance, and you've encountered this also, I think. Optimizing for performance is not easy, especially in the presence of these three different bottlenecks. And you didn't even have those bottlenecks here in this problem, right? OK, so much of parallel computer architecture is actually about designing machines that overcome these bottlenecks to achieve higher performance and efficiency, both sequential and parallel bottlenecks, and also making parallel programmers' job easier in writing correct and high-performance parallel programs. And we will cover these two. And these two are actually interrelated. If you design a machine that can execute the sequential portion very fast, then the programmer doesn't need to invest a lot of time or thinking into reducing that sequential portion. If you design a machine that can handle the bottlenecks in the parallel portion, synchronization better, load imbalance better, and resource contention better, then the programmer doesn't need to even think about those things. Right? When the programmer needs to deal with those issues, that's when bugs happen, and because they try to optimize for performance at that point. Right? OK. So how do you alleviate some of the serial and parallel bottlenecks in a multi-core processor? We'll return to this question in the next few lectures, but you'll have a good reading list. Don't worry, you're not going to do reviews on all of these, but you're going to do reviews on a selected part. I'd recommend you to look at some of these things. And a lot of these papers talk about having different types of cores. So you can have, if you have lots of parallelism in your parallel portion, you can execute your parallel portion in simple cores. But if you don't have a lot of parallelism, you really need the large cores to execute fast and get out of that serial part. If you've designed a machine that only has very simple cores and that cannot execute the serial part fast, then you have a problem. Now you're relying on the programmer to minimize that serial part, because your machine is not doing anything about that serial part. Right? If your machine is doing something about that serial part, your programmer's life gets easier. And these papers talk about that. And I'd recommend you to look at that. And you can do projects related to this. And I think this is a very fruitful area of research, actually. How do you accelerate I think serial part is relatively easy. But there are research topics related to that also. Because how do you actually design the core that accelerates the serial part? But the parallel bottlenecks is also interesting. Like, how do you accelerate the parallel part, bottlenecks in the parallel part? And one theoretical potential research project is, if you're interested, Amdahl's law doesn't consider the bottlenecks in the parallel portion, right? So we don't even have an intuitive model to think about the parallel portion. Amdahl's law is great because it has this abstraction, sequential versus parallel. And we can think about, oh, my sequential portion is this much. And you could actually quantify this for a lot of programs. But what about the parallel portion? How do synchronization, load imbalance, and resource contention actually affect parallel speedup? We don't have an intuitive model at this point. Can we develop an intuitive model to reason about these? And I think this is a very interesting research topic. There are some papers that try to tackle this, although they're not fully successful. But these are a good place to start, because they haven't fully covered all of the bottlenecks. But I would recommend you to take a look at these. And Han will put these up, just like he does every single paper. But if you're interested in it, this is an important and difficult research problem. Basically, we need better analysis of not only critical sections, but also these different reasons why parallel part is not perfectly parallel in real programs. And that could be one project, for example. You could take some real programs, analyze these bottlenecks in the parallel portion, and try to develop a model, intuitive model, that actually covers that. And that would be something that at least no one has successfully done so far. OK. But I'll give you some other papers to review, if you will. And those will be related to what we've talked about. And hopefully this is a good series of papers that you may or may not have already read if you've taken my classes. We've certainly discussed this in both 447 and 740. And actually, we did discuss this in 740. But this is the latest work that we've done in the area that is more general. So I guess 3 reviews, that's not too bad, right? No, I don't hear a whole lot of enthusiasm, but hopefully it should be exciting. OK, so this is the September 16th. And we'll give you the literature survey and research project handouts sometime during this week also. But this will help the lectures also, because I'm going to cover some of these papers If not earlier than September 16th, later than September 16th. So you'll have good background. And you can actually cheat and look at the last year's lectures to get an idea of what these papers are about. But I would still expect you to read the papers. Okay. I think we'll stop here. Any questions? No? Do you guys want to continue instead? No, let's stop here. I guess I'll see you.